So in this video, I want to just review what a sampling distribution for difference of two proportions coming from independent populations looks like, and then we'll talk about how we could apply the sampling distribution, the theory of the sampling distribution, to help us do hypothesis tests for difference of two proportions. So just to back up, back in chapter 4, we did take a look at sampling distributions for the difference of proportions. Okay, and so let's say we've got two populations. So population number 1 has some proportion of the population, P1, which is a success. So maybe they responded yes on a survey or something like that. And then we have another population, and it has a different proportion, maybe, for its population. And then these values N1 and N2 over here, this would correspond to the number of people that we include in sample 1 from one of our populations, and then the other N2 would be the size of our second sample. And X is denoting the number of successes that we get from the first binomial distribution, and Y is denoting the number of successes that we get from sample number 2. And so then we know that the sampling distribution for the difference in sample proportions is going to have the following properties. So first we want to know, where is that sampling distribution going to be centered? What's the expected value for that? And we can break up sums and differences inside the expected value. So it would just be the difference in our population proportions. Next, we'd want to find the variance for the difference in these proportions. When we break up the difference of the variance, that minus 1, when it comes out from the variance, is squared. So that's why we get an addition over here. And then we've talked about how we can find the variance for the distribution of a proportion. So this would be the variance for p hat 1, and here's the variance for p hat, that should be a 2, for p hat sub 2 over here, and therefore adding the 2 gives us the variance for the difference in the sample proportions. So altogether, the central limit theorem tells us that the distribution is going to be normal. Here it's going to be centered at the difference in the population proportions, and we've got a formula for calculating the standard error of that distribution. Okay, so in this video, let's see how we can apply the results that we know from the central limit theorem for a difference of two proportions. How can we use that to calculate test statistic and p-values when we're doing a hypothesis test for a difference in two proportions? So step 1 is set up our hypotheses, and for the null hypothesis, we're always going to be claiming in the null that the difference in the two proportions is 0, that there's no difference between our two populations. And the alternative is going to be something interesting, like there is some difference between the proportions of these two populations. So it might be just simply that the proportions are different from each other. It might be that one is less than the other, or one is greater than the other. So that's how we would set up our hypotheses, which we've discussed. Then we collect data from our sample, and then we want to see how extreme is our sample data compared to the null hypothesis. So this test statistic is a way of standardizing the distance of the sample from the claim in the null hypothesis. So our sample is going to be that p hat 1 minus p hat 2. So here's the observed difference that we get. And then we're going to compare this to what we claimed this difference is in the null hypothesis. And in the null hypothesis, we're always going to be claiming that there's no difference between these two groups. So this difference of p1 minus p2 is always going to be 0. And so we get some difference, and then we don't know whether that difference is within what's reasonable variability from sampling, which is measured with the standard error, or whether this difference seems to be beyond what we might expect from the whatever difference we might expect just due to the sampling alone. So then, using the central limit theorem from the previous slide, we can approximate, or actually we know that in theory the standard error is given precisely by the square root of p1 times 1 minus p1 over n1 plus p2 times 1 minus p2 over n2. But we don't know what p1 and p2 are. That's the whole point here. So what we typically have done is plugged in values for p hat 1 and p hat 2 into each of these separately. But let's keep in mind that p hat 1 and p hat 2 are different from each other. So we usually calculate this test statistic under the assumption in the null hypothesis. And so the null hypothesis says that whatever I pick over here should be the same as what I pick over here, because this value and this value are the same. So we want to come up with an estimate for what P1 and P2 should be, and there's no claim about that in the null other than that they should be equal to each other. So we're going to approximate P1 and P2 in this calculation with the same value, and that value is going to be what's called the pooled proportion. So I'm going to denote that with a p hat p. And so what that means is we're going to group together how many successes were there from group 1 and group 2. Let's add those together, and then let's divide by how many people were there altogether. So if the assumption is that these two proportions are equal to each other, then what we're saying is there's not really any difference in these two groups. And so let's just pool them together and calculate and approximate what these individual proportions are with what the pooled proportions are. So when we do that, here's the resulting formula that we can use to calculate our test statistic when we're working with proportions. And so notice what happened in this formula is if we're using the same values for P1 and P2, namely P hat P, we could just pull this out from both of these fractions. And so we can multiply the pooled proportion times 1 minus the pooled proportion times the quantity 1 over n plus 1 plus 1 over n plus 2. So it's a slightly complicated looking formula that you just want to be careful with how you enter things into a calculator or however you're computing this. But that's how we can calculate the test statistic. So basically what we're doing when we do this calculation is we're approximating how many standard deviations, how many standard errors from the sampling distribution is our observed difference in sample proportions from the claim that there should be no difference. And then when we calculate the p-value for this, we're going to use a standard normal distribution. So we've standardized the distance of our observed sample from the null claim. And just like with t-tests, we do have a command in R that will do this for us. So in other words, it's going to save us the trouble of this calculation called the prop test. So we used this when we had confidence intervals, but now we're going to leave off that conf at the end here because we want to see the details of the test. So if we're comparing two populations, then I put number of successes from sample 1, number of successes from sample 2, number of observations from sample 1, number of observations from sample 2, and then over here we would put 2 tail or greater or less depending on the alternative hypothesis. So here kind of a new ingredient is what do we use to approximate the proportions in the standard error if there are no claims about P1 and P2 individually. Rather, the claim is that these should be the same. Then we're going to use the pooled proportion to approximate both of them, which is consistent with our claim over here. So that's the theory, the background behind how we're going to find these test statistics. So let's take a look at an example on the next slide.